I might have to leave.
Okay.
Okay, so yeah, okay, so we are very happy to have Sushant Sachdeva with us. Sushant is a faculty member at University of Toronto. He was a PhD student at Princeton a while back, and followed by a postdoc stay at Yale. He moved to Toronto. Sushant works in algorithms, all things algorithms, because optimization, machine learning, statistics. Okay, and he's going to tell us about their brand new algorithm for Max.
Thanks for that, and thank you for coming. It's great to be here. Good. So I'll talk about our recent, maybe slightly not so recent, but an enormous linear time algorithm for maximum flow and many other problems. This joint work with amazing collaborators: Lee, Rasmus, Yaman, Richard, and Max. It's all a COVID Zoom collaboration all the way through and through. Good. So let's talk of max flow. It's a problem all of us have seen in an algorithm course. It's a convex. So it's a classic graph optimization problem. Here's a citation back from 1950, if I'm right, 55, trying to formulate the capacity of the Soviet railway network as a max flow problem. So it's been studied for almost 70 years. And why? Because it's a powerful framework for capturing many variants of graph optimization problems. And it's been a challenge to design faster algorithms. We've stuck ahead to the 1.5 for a long time. So it's been a test bed for development of many new techniques over the past 2 decades, especially in algorithm design. And right, so we will talk about finally designing an almost linear time algorithm for this problem. So just to remind us of what is the setup, we will talk about directed graphs. So your vertices, M edges and vertices. The 2 special vertices, the source S and a sink T. Every edge has a capacity, right? So we'll denote the capacities by UE. And for simplicity, assume it's an integer between 0 and polynomial, right? So some polynomially large in M and M. So for example, so in this graph, we have a source here, we have a sink here. These numbers indicate capacities, and you have. I should stand here. Is that
No, it should.
What's
That's
the,
it. So let me just see if I can increase the volume.
That's pretty high already. Maybe you want to go automatically.
Next thing here.
Yeah, what now?
Okay.
How about now? I think that's much higher.
Now can you hear
But the chat can confirm. Now can you hear it better now?
Only slightly better.
Slightly better.
So, we are not using this.
No,
we are.
Oh, but then that was not the mic in your audio settings. This is a different mic.
Oh, sorry.
Yeah. Oh, it's using. Can you use microphone 3?
Oh,
It's just
sorry.
How about now, Rahul?
Yeah, it's similar.
Actually, it's not bad at all. It's quite clear.
Okay. So Kavita says it's quite clear.
Yeah, I can hear Kavita very well. Not.
We want to check the mic.
No, but I think now it should be okay. I mean, like
Yeah, carry
we
on.
were on the wrong mic.
Is it clearer now, Rahul?
Yeah.
Okay, good. Yeah, we are on the wrong
Sorry.
line. No worries. Okay, thanks, Rahul. Good. So here we have S and T. The edges have directions, right? On every edge, you can flow along the direction and up to the capacity. Okay, so let's just formalize that. So okay.
So you'll have to just click on your screen.
Right. So what is our goal? Our goal is to route the maximum amount of flow from the source S to the sink T, respecting your directions, right? You're allowed to flow along the direction and upper bounded by capacity, right? so subject to your capacities. The classic view of this problem has been to think of flow paths, right? Combinatorially, right? Every time you pick a path from S to T, here's one path, and I will send 1 unit of flow along this path. And you pick a collection of paths. Here's the second one, sending 1. Here's another one, sending 1. You put these together, and you get a flow from S to T. But we will deal with a linear algebraic view of flows. So, what is the linear algebraic view of flows? Is that you assign a flow value to every edge. And this flow value, so here are values in purple. Which of these vectors capture flows? We need two kinds of constraints. The first is we want capacity and direction constraints. So you want the flow Fe to be between, it should be non-negative and bounded by the capacity on the edge, right? These are the easy ones. The interesting ones are flow conservation constraints. So to do that, let me add a special edge back from the sink to the source. Okay, and on this edge, I will put a flow value that's equal to the sum coming into the sink, right? So 1 plus 1 plus 3, 5 back to the source. Now I can ask that at every vertex, inflow is exactly equal to outflow, right? And that's my conservation constraint or flow constraint. So now all of these constraints together, they capture what is a flow vector. And your goal is to now round maximum amount of flow on the special edge. This is exactly the max flow problem. Right? Everybody with me? Okay, good. So this is a linear program, right? The way I described it to you, it's exactly a linear program that I'm going to maximize the flow on Fe sharp or minimize minus Fe sharp equivalently. You have directionality and capacity constraints, and I have conservation constraints, one for every vertex, where inflow equals outflow. Right? And the key result is that we can solve this linear programming perspective of max flow in almost linear time. Right? I'm hiding, like, since I assumed the capacities are polynomial, I'm hiding the dependencies, but on capacities, but those are polylog dependencies, like log squared. We can solve a much more general class of problems here, not just max flow. We can solve all convex flows. What are convex flows? That I have a flow which still satisfies direction and capacity and demand constraints, but now I'm allowed any separable convex function on the flows. So I have for every edge, you specify a cost function, cost of E, that just depends on Fe. Can be any convex function on that edge. You sum these over these edges, and we can minimize these flows in almost linear. We can compute flows that minimize this cost in almost linear time. Right? And this is a very powerful term. Yeah.
Change the conservation, the zero change to a T. No?
Good. You can also do arbitrary demands at every vertex.
Okay.
Yeah, slightly more general. Could have been zero.
It could be compact.
Yeah, every vertex can send in some flow, can take out some flow, and it can still solve. Right. I mean, there's a fairly easy sort of reduction by just taking one initial solution. Right. So now this framework actually captures a lot of well-studied problems and gives you almost linear time algorithms for the first time, say for bipartite matching, min cost bipartite matching, min cost flow, negative edge shortest paths, worker assignment, optimal transport. These all actually just follow from reduction from min cost flow. But the general convex flow framework gives you even more. It gives you matrix scaling, phenom flows, entropy-regularized optimal transport, which has been it's been pretty hot in sort of theoretical machine learning, trying to map distances between distributions. Right, we get almost linear time algorithms for all of these problems. And my goal here today is to try to give you 2 to 3 key ideas that go into these results. Right? All right. So before I go into the key ideas, I'm going to just take one slide retrospective on all the works of max flow. Right? There is a lot. I cannot do justice to the amount of work, but I want to sort of put it in perspective in terms of different paradigms of algorithms that were being developed. So the first phase really, for a long time, was viewing these problems combinatorially. Think of them as a collection of paths, and you add collection of paths, and you get them, and you sort of add them up together. I want to describe them in terms of combinatorial outer and inner algorithms. What do I mean by that? So all of you have probably seen Ford-Fulkerson. Find an augmenting path, send as much as you can, construct the residual graph and repeat. I want to split that algorithm as an outer algorithm and an inner algorithm. The inner algorithm is just find an augmenting path, right? And the outer algorithm says construct the residual graph, right? And then sort of ships it to the inner algorithm. So there's an outer algorithm, there's an inner algorithm. And actually, you will see the structure repeating in every max flow algorithm that you use. So for a long time, there was sort of almost no distinction. These were all both combinatorial inner and outer algorithms, and this led to the famous work of Goldman and Rao achieving m to the 1.5 running time in 98. Since then, for a long time, there was no progress on the running time bound in some sense. But 10 years later, Deitch and Spielman gave a different approach to achieve the same m to the 1.5 bound. They replaced the outer combinatorial algorithm with an interior point method, which is now a numerical optimization algorithm. And the inner problem then also became a numerical problem computing electrical flows. Okay, so
the inner problem was the augmenting path. What was the outer problem?
Was the outer was just looping over it while constructing the residual. At every iteration, you construct a residual graph. You got back the augmenting path. This also applies if you've seen blocking flows, right? At every iteration, you got a residual graph. Now compute a blocking flow. I add it back and I compute a new residual graph and then compute a blocking flow. So all of them sort of call. Right, so Deitch and Spielman introduced the idea that you can think of these problems in terms of numerical algorithms also, numerical optimization algorithms. And they achieved the same m to the 1.5 bound way by combining interior point methods with the work of Spielman and Teng that gave electrical flows in almost later time. If you haven't seen them, don't worry about it. We will not need it later, but if you're aware of it, I want to put it in context. This was new for min cost flow. This was the first work that achieved m to the 1.5 for min cost flow. Before that, we had only known m squared for min cost, mn for min cost flow. From here on, all the progress in max flow has been based on combining numerical algorithms or numerical, right, like taking this numerical algorithms view. And all of that progress actually uses interior point methods as the outer loop. And these outer loop requires root m or fewer iterations, right? M to the 1.5 or fewer iterations. And for many works, they were making progress on the outer loop. Let's reduce these number of outer iterations. Finally, we got down to something like m to the 1/3 outer iterations. Okay. In the last couple of years, right? So outer iterations, we are sort of stuck at we got to m to the 1/3 for some cases, for unit capacity cases. But the inner problem is still linear time. So at best, you can hope for m to the 4/3 here. So recently, there were a couple of works trying to reduce the cost of the inner problem by trying to use some data structure. They got a hairline below m to the 1.5 for general maximum. Why am I telling you this story? Because I want to contrast the work. How does it fit into the story? So we achieve almost linear time, but how do we do it? We still take a numerical outer algorithm, an interior point method, but it's a slower outer algorithm. It's an algorithm that requires almost linear number of iterations. But what is the advantage of a slower IPM compared to all of these works is that we get a combinatorial inner problem. And we are able to amortize it over all the iterations. We are able to give a fast dynamic algorithm for solving the sequence of combinatorial problems. Okay, and together that gives us an almost linear. Questions?
So all of these things, irrespective of the relationship between m and n, it's still m to the 1+.
Yeah. Let's just think of sparse graphs. Sparse graphs have been a big bottleneck for us, and just think of m as roughly. So we knew m to the m to the 1.33, but only in unit capacity cases.
Okay.
If your capacities were large, the best was this 1.48. All right, so good. So I want to tell you about sort of two key ingredients that go into this piece, our outer and inner algorithm. So the first is our outer algorithm. This is an L1 interior point method. How many of you have seen an interior point method at some point? Okay, so I will try to give you a visual introduction. So hopefully it will be fairly followable. So interior point methods are a general recipe to solve convex programs, or I'll just focus on linear programs. So here's a linear program. This is my polytope, and over this polytope, I wish to optimize along this cost direction. Right. So here's a potential reduction IPM, one of the first ones that was given by Karmakar, 1984. He devised this following potential function, which is a sum of two terms. There's a first term, this one. It decreases, these are all logarithmic terms. The first one is a log term that improves in the direction of the cost function. Okay, you guess the optimal value, right? Let's say the optimum is 1, and you log of the current objective minus 1. So it's a log objective that improves in the direction of the cost function. And there's a second term, 1 for every constraint, right? So 1 for every edge. That's enforcing that you stay far from each of the boundaries. Right? So for every edge, I add a log FE term that says that FE stays far from 0. And I'll add a log capacity minus flow term that says you stay somewhat far from the capacity. You add all of these terms together, you get a convex concave objective, right? It's not a convex objective, right? You get a convex concave objective on the entire polytope. I don't know if you can see the size very clearly. There's a gradient in the direction of the cost function, and it keeps you away from the boundary sum. Right? And the entire algorithm is that you start from an F0 point here, you keep moving locally, improving your objective slowly. You move to F1, F2, F3, all the way. As you keep moving the objective, at the end you will end up close to a vertex, and you round it. Right? That's how you solve a linear program using integral methods. Okay, so all I need to tell you now is how do you take these local steps? How do you move from Fi to Fi plus 1? Okay, so I am at, let me describe that. So let's say I'm currently at a flow F. I want to move to a next step. Let me denote it by F plus delta. Delta is the step I'm going to move. How do we find this delta? So the way we're going to do it is, remember we have a potential function that we are trying to improve, right? The way I'll do it is that locally I'll write a second order approximation to the potential function, right? So you have the potential at the current point, it's a second order Taylor approximation. You have potential at the current point, you get a gradient term with the step, and you have a second order term. I've written it in a funny way rather than writing it as a Hessian term with delta square. I've written it as L delta square. Let me explain that for just a second. So the Hessian, remember the Hessian had log terms for the flows. They're all separable, right? Like every FE just has one term. They don't interact. So when you take the Hessian, you get a diagonal Hessian in terms of the flow variables. Right? It's a diagonal Hessian. So I'm just writing it as there are these lengths for each of these edges, which is the term in the diagonal square root, and length L delta squared, right? The 2 norm squared. So this is sum over E LE delta E squared. LE squared delta E squared.
So you don't have cross terms because of the form of the function.
Because of the form of the object. That's right. So there are cross terms in the first one. They are actually negligible. You completely ignore the Hessian of the first term. You only take the Hessian of the second term. There are no cross terms. You get a diagonal, and I'm just rewriting it as L delta squared. Is everybody with me on this way? And what is this form of the length? This is what I guess is somebody monitoring? If that question, there'll be questions on the chat. We'll see that.
Sure.
Yeah. Okay. So this length turns out to be interesting. This length is the inverse symmetrized residual capacity. So it's 1 over Fe. So remember, what was the constraint? Fe has to lie between 0 and UE. So how far is Fe from 0? Just Fe. So it's 1 over Fe. And how far is Fe from UE? 1 over, like it's UE minus Fe. So it's 1 over UE minus Fe. And you take the one that gives you a harder constraint. So you take 1 over the minimum of the two gaps, two slacks. That sort of, this is assigning lengths to your edges. A large length means you are very close to that constraint, and I'm going to penalize that flow on that length very hard. Right? And smaller length means a less constraint, you are more free to. Right? Good. So after you write this Taylor expansion, now the standard Karmakar IPM says that you minimize this over delta, feasible delta. What are feasible delta? Feasible delta are that steps that will not change my linear constraints. Remember, I had these linear constraints for flow conservation, linear inequalities, right? All the inequalities went into the potential function. I'm only left with equalities. I want the conservation, the net flow at the vertices to not change, right? So I want delta, which are circulations. So the net flow at every vertex is 0. Subject to that, I'm going to optimize this second order approximation, right? Good, and that gives me the electrical flow problem, which is minimize over circulations, a gradient contribution, G transpose delta, divided by the L2 length of L delta. This problem is an electrical flow problem. You assign resistances to each of your edges and you compute an electrical flow over this graph. This is the standard Karmakar IPM. But this is not what we'll do. We're going to modify this. But let me just visualize what this does. So this problem puts an ellipsoid around your current point. You have a direction given by the gradient, and subject to being inside the ellipsoid, you optimize the gradient. And that gives you your next step, F plus delta.
Karmakar ellipsoid not centrally symmetric, they are shifted. Karmakar ellipsoid.
No, why?
We take this projective transformation, which will move the.
But the projective transformation here, because of the constraint, is just sort of scaling the. Like this is giving you the projective transformation. The lengths. Yeah, no, I think they're symmetric.
So Karmakar's algorithm is more than just max flow setting, right?
Yeah, any linear program. All of this that I'm describing to you is for any linear program. Yeah.
Only the form of L here is like specific.
Yeah, because that's right. Because there is no interaction. But this general geometric picture is applicable to any linear program. Okay, so we are going to change this. We define an L1 IPM. What is that? So instead of the L2 squared contribution that we got from the Hessian, I'm going to upper bound it with the square of the L1 norm. Right? It's strictly larger. I'm taking a strictly worse upper bound. And I'm going to optimize that upper bound. This results in a different step problem. What is the step problem now? Is I packed an L1 ball inside the ellipsoid, and you want to move to the vertex of this L1 ball that gives you the best objective, right? So in this example, here's how I'll look at it. The problem that we now get is seeking to minimize over circulations still the ratio of the gradient term over the L1 length of the cycle, L1 length of the flow. Right? Instead of measuring the length of the flow as L2, I'm measuring it as L1. So, and this is a problem we call the mean ratio cycle. Okay.
This you can't do for linear programs generally, or just
the problem becomes more intricate. It's much in graphs you can interpret that problem very easily, right? You can write the same thing for general linear program, but it's not easy to interpret the problem because there's no easy kernel space. There's no easy basis for the kernel space.
And you no longer have that electrical flow condition. You
no longer have the electric. These are not electric flows. No. Right? These are no longer. So let's just talk of what is this problem. Yeah.
One in which before they have one, before they have one. Yeah, okay.
Right. So from L2 length, we change to L1.
So here in something, the denominator is like measuring energy or something.
That's
So that's why you get electrical flows. But
That's right.
is there a physical interpretation of what L1 is supposed to capture?
It's just the length of the flow, right? Like so.
Okay.
So let's just take
Okay.
1 second to actually interpret the problem, and then I'm happy to come back to the question. So let me take an example, right? Here's a graph. On the graph, every edge has a length, right? These are numbers in red. These are lengths. Also, every edge has a gradient term, right? So the gradient term here are black numbers in black give you the gradient term. Gradient terms come with directions. I want to stress that, right? So a flow moving in this direction, let's say from this red vertex to this red vertex, has a positive 4 contribution gradient. If you go against the direction of the gradient, you get a -4 contribution. Right. So let's just descend 1 unit of cycle, 1 unit of flow along this cycle. So the length contribution is very easy to count. You just add up the red numbers, right? You get 1, 2, 1 plus 2 plus 1 plus 2, that's 6. The gradient contribution, you have to check whether you are flowing along the gradient or against the gradient. Right? This one, I'm flowing against the gradient, so I get a -4 contribution. This one, I'm flowing against the gradient, so I get a +1 contribution. Again, against the gradient, I get +3. Along the gradient, I get +1. You add these numbers, you get +1. Right? If I was to flip the direction of the flow, the gradient term changes sign, but the length term remains the same. Right? So I want to stress that edges and lengths are undirected. On an edge, you can send flow in either directions. There's no hard constraint. However, your gradient contribution depends on the direction that you're going to travel with. Right? In that sense, it's an intermediate problem between directed and undirected graphs. There are no hard constraints, but your contributions depend on the direction that you travel. Does this answer the question? Okay. So this is the mean ratio cycle problem. That is our inner problem now that we need to solve at every iteration. Right? And here's what is the advantage of going to this L1 IPM? Here's at least I can give you a very, very simple advantage. Now there is an optimal solution that's very easy to describe. There is a simple cycle in the graph that is an optimal solution to your problem. Rather than having an electrical flow which is non-zero everywhere. Now there's a simple cycle in the graph that achieves an optimal solution.
This is because of linearity.
Yes, just linearity.
That's the algorithm. You find minimum ratio cycles, flow in it, and keep on.
Good, but what is the running time of that algorithm? How do you find? So you need m outer iterations. At every iteration, even if I just read the graph and the numbers, that's m times. So that's m squared. Right? So you need. So we are going to do the inner steps almost constant time, very, very quickly. Amortized.
Because cycles could be long, but I suppose
That's right.
one of the algorithm
Your cycles could be very long. At every iteration, your cycle could be long. You still have to be able to find them and update them in almost constant.
So you have to iterate over all the cycles, or
no? If you do that, that's too expensive. Let's go to the running time in just a second. Right. So right now, let's not go. Right now, I just want to talk about the IPM and the structure of the algorithm. Is that clear? I'll talk about how do we solve the cycles a little in just a bit. Okay, so here's a theorem about the L1 IPM, which are mostly sort of let me just summarize it as a theorem. So we give an IPM for max flow that is as follows. It requires almost linear number of iterations. At each iteration, you have a sub-problem that is a min ratio cycle. So you get new gradients and lengths at every iteration, and you want to solve the min ratio cycle problem for these gradients and lengths. You don't have to solve the problem exactly. At every iteration, if you solve it to some approximation, let's say, like log n approximation, that's good enough. Or even sub-polynomial approximation is good enough. You pay that in the running time a little bit. And third, and this is crucial, is that if these were all independent problems, then we are toast, right? Because there's just too much information for us to process. These gradients and lengths don't change dramatically. In fact, over all of these problems, like going from one problem to the next one, only a constant number of them change. right? That's essential. Otherwise, we just can't even read the input, right? So the problems are changing slowly. Not only are the problems changing slowly, we actually know there is a good solution hidden, unknown good solution that's the same throughout the process. So what does that mean? For each of these mean ratio cycle problems, the direction to the unknown optimal max flow, F star. So from F to F star, look at the direction from F to F star, that represents a good circulation for any of these mean ratio cycles. Right? So there's a hidden fixed good solution that's a good solution to all of these, right? And this will also be essential for us to find. Right? Is the theorem clear to all of us? Okay, good. So that's what I wanted to talk. Okay, we started 2:35. Okay, so we're pretty good time. Okay, happy to take questions if there are any at this point.
So in the first thing of Karmaka, you mentioned that we needed to know opt. In that we need to know opt.
Oh, that's right. That's just a binary search. Opt value,
Yeah.
not the
Yeah, I
opt.
know.
Right.
But here you don't need.
So no, we will assume that you've binary searched and you know the flow value. Right. Yeah, we'll assume you guessed the flow value. Yeah, we do need to know it. Otherwise, we don't know how to write the log variable objective. Okay, great. So that's about the L1 IPM. Now I want to talk of how do we solve these problems, these mean ratio cycle problems. And this is a second key ingredient, which is a mean ratio cycle data structure. And this forms a inner algorithm, right? So just drawing that analogy, our L1 IPM is the outer algorithm, and the data structure for solving the mean ratio cycles is the inner. Okay, so I'm not sure how many details about the mean ratio cycle data structure I'll be able to give, but let me first try to convince you that L1 is nice, and I will show that by showing that we can solve it approximately by using some tree approximations for the graph. Okay, so I'm going to first show you how to just solve one instance of mean ratio cycle. So what is our goal? So you're given a gradient G, you're given length L, and your goal is to solve this mean ratio cycle instance. Find the circulation that minimizes G transpose delta by the length of delta. Here's my algorithm. My algorithm is very simple. It's going to sample a random low stretch spanning tree. If you haven't seen low stretch spanning trees, don't worry. I will tell you what they do, but it's a particular type of distribution on trees, spanning trees on the graph. I'm going to sample one low stretch spanning tree. And then I'm just going to, this can be done in almost linear time. This is well known. I'm going to just check all fundamental cycles of this tree. What does that mean? You take a single off tree edge, you look at the unique cycle you get by adding it to the tree, check all of these fundamental cycles and return the best one. Right? With some dynamic programming, this can also be done in almost linear time, even though there are m cycles. But now I will tell you why this actually returns to you a good approximation. Okay, so we'll do that visually. So my claim is that actually some fundamental cycle in the tree is a polylog approximation to your mean ratio cycle object. So let's say here's a graph I'm working with, right? In blue is my low stretch spanning tree. Okay, what is a low stretch spanning tree and what is the guarantee of a low stretch spanning tree from this distribution? Let me tell you that. So this sampling from this distribution on low stretch spanning trees guarantees the following. Guarantees that if you pick any edge E that's not on the tree, let's say, right? So say here, thick black edge. Look at the fundamental cycle of that edge. That's this thick black edge and these two thick blue edges. The length of this fundamental cycle is not much larger than the length of the edge. some polylog factor. Let me ignore that for. So the length of the fundamental cycle is not much larger than the length of the edge. And this is an expectation over the distribution on trees. Fix any edge, sample a tree. In expectation, the length of the fundamental cycle is not much larger. This is your guarantee from the distribution.
The edge was on
The edge was not on the tree.
how is that? You fix an edge and then you're picking over spanning trees which.
Yeah, okay. So if it is already on the tree, then it's just a trivial.
So in some sense, you want to say that the tree distance is more or less going to approximate distance between any pair of it.
That's right.
Okay,
Yeah,
that's right.
fair enough, yeah.
But it can't do everything, right? If you
Yeah.
do the cycle, something is.
That's right.
But on random, right? Like so, if you fix an edge, you randomly, we are good. So if it's on the, you just go and come back. Right?
Okay.
Like that's the. Right. So this is the guarantee of the spanning tree distribution.
What's the low state spanning tree?
A low state spanning tree, a distribution of low state spanning tree is almost. This is almost exactly the definition of sampling from this distribution. It says that any edge that's not on the tree, its cycle in the tree is not too large in expectation. That's the distribution.
But I guess the non-trivial part is that such a distribution exists,
Yes.
and that you can sample from.
And then you can sample it in the. These both facts are non-trivial, but the non-trivial but well known now for now. I mean, I don't care this to be a bad approximation. If you didn't care about this approximation, this has now been known for almost 30 years. Alan Carter is best. Right, so such trees exist. We can sample from them. Now, let me show you that this guarantee gives you something nice about the approximation. So let's say here is in green is my hidden unknown optimal solution for the mean ratio cycle. Right? I don't know it, but for the sake of proof, let's say this is my set. Let me now apply the guarantee that the low state spanning tree gives me to all the edges in this cycle. Right? So I sum over my edges in the optimal solution. The expected length of fundamental cycles of each of these is not too long, is not much longer than the sum of their lengths, which is L delta. Right? I've just applied the guarantee to each of these edges. And this is linear, so I've just applied it in expectation. Now, just apply my linearity, collect it. So, in expectation, the sum of the length of the fundamental cycles is not too large. So, by Markov, it's not too large with probability half. Right? I've lost the factor. Good. So, the sum of the lengths is not too large than the original length. But actually, let's look at the gradient terms. The sum of the gradient terms actually is exactly the same. Why? Because if I look at these fundamental cycles and send 1 unit of flow along all of them, all the tree edges cancel perfectly. Right? All the tree edges cancel perfectly. You're only left with your mean ratio cycle in the green. Right? So sum of gradient contributions along your fundamental cycle exactly adds up to the gradient contribution of your optimal solution. So the sum of gradient contributions is the same. The sum of lengths is not much larger. So by averaging, there is a solution that's not much worse. Only worse by a polylog factor. Right? But this was with probability half. You repeat it log n times and you pick the best solution you found with high probability of the solution. Right? Questions? All of you with me? Right, so what does this show you? This actually establishes an advantage of going to L2 already, right? Also going from L2 to L1. Since this was an L1 problem, we actually know how to approximate L1 lengths in graphs very nicely using trees. And when you do that, just looking at these tree cycles helps you find good solutions. Okay, so now with this idea, what's remaining is the meat of this problem. Like, how do you maintain these trees very quickly and still be able to find such solutions over time? Right, and that I guess how much detail am I going to go into will depend on how much time we have left. But let me first tell you what is the theorem we show. So we build a mean ratio cycle data structure that does the following. So it's a randomized data structure that maintains a small set of spanning trees. These, like on these spanning trees, very quickly, very efficiently, we can support the following operations in efficient amortized time. First is change gradients in length, right? So our construction of spanning tree only depends on the length, right? But with cycle, your output does depend on the gradients, right? So I have to allow you a procedure that changes this collection given updates to gradients and lengths. That can be done efficiently. Can return an approximation to the best mean ratio cycle. Right, I shouldn't say the best technically. It's comparable to the hidden solution that you got. Small technical distinction there. Right. So remember, this cycle actually can be large. We want to return it very efficiently, but because these are trees, we actually have a very efficient basis for representing these cycles. Right. It's some fundamental cycle of one of these trees. So I just give you an off tree edge, and that gives you the cycle. And finally, because these are trees, we can update flow along them efficiently by using some recursive tree data structures. Right? We can do all of these operations. We can't do them for a worst case collection sequence of problems. We can only do them for the kinds of problems that appear from our IPM instance. And the key thing that we exploit is that there is a fixed hidden solution that I highlighted at the sequence. So that turns out to be essential to designing this data structure for us. Right? Any questions so far? Okay, so we do have time. We have 10-15 minutes. And yes.
So what do you mean by that was there in the previous theorem, the fixed one? So where is that condition?
I sort of didn't write it, but for this data structure to guarantee that it actually finds.
That's a part of the hypothesis.
Yeah, it's a part of the hypothesis.
Okay.
All right. We assume that these problems have a common hidden solution.
Okay.
And it's exactly of this form, f star minus f, and then we can continue to. And also the other technicality is we can't answer an approximate solution compared to the best one, but we can answer it compared to the single fixed hidden solution. Right? Right. In the previous one, I only said there is a good hidden solution. I didn't guarantee that that's the best solution. You could accidentally run into a place where there is a much better another solution. But we don't want to compare to that.
In what sense does it need access to that fixed solution? You just need the existence of
You just need the existence. Yeah. No access. We just need the existence. We just need that f star minus f is there is an f star unknown that f star minus f represents.
So this sequence of problems, they all have the same solution.
Yeah, they all have a single fixed.
So then this algorithm works well amortized over those.
That's right. That's right. Okay, so we have, I don't know how long do you typically go, but we have
20-25 minutes.
Oh, okay, yeah, okay, good. So then we can talk of the data structure and the key ideas of the data structure. Good, but now I'm going to go into more technical details. So let's
get spare time. You can give some intuition as to why these load state cycles are easy to sample randomly. Here, they
You mean low state spanning trees?
Yeah, yeah.
Good.
One side you should like that.
Yeah, I am not sure I can. I can.
Yeah. That's an off-the-shelf thing.
Yeah, it's basically almost. So, like in fact, a lot. Okay, I guess I don't listen here. Lots of works starting from it. AKPW. So right, so like this one, ESTI. So I can describe to you, I think, informally how to construct a single one, but the distribution requires. But a single one maybe I have time. I mean, a single one AKPW is also very nice. Okay, good. So let's talk of the data set. Good. So first, let me just summarize now. How does, at a high level, what does our overall algorithm look like? So our overall algorithm initializes a data structure that maintains a small collection of trees, and then sort of go into an iterative loop. This is our outer algorithm where you have almost linear number of iterations. At every iterations, you get gradients and lengths that are changing slowly. So you update your gradients and lengths. From these lengths, you update your collection of trees, right? So as the lengths change, the trees also have to change, right? The trees are based on these lengths. So you update your collection of trees. Now your data structure identifies a circulation. That's an approximately good solution to this mean ratio cycle. Use that to update the flow and then repeat. I mean, alpha is just some scaling factor. So you send some fixed amount of flow along the cycle and you repeat. This is our entire algorithm. Good. So let's talk of how do you get a data structure that can actually do this efficiently. So there are sort of two ideas to the data structure. One is a vertex reduction idea, and one is an edge reduction idea. I'm going to first motivate the vertex reduction idea. So let's think of the following setting. Let's say the first iteration, you got length, you computed, let's say for the sake of argument, let's just say you found one good spanning tree, right? You found a cycle, you could go to the second iteration. Now some lengths have changed. Okay, I need to update the tree for this change in length, right? But I don't want to pay the entire cost of recomputing the entire tree, right? That's going to be too costly. Can I save work by using the previous tree, modifying it so that I don't have to do all the work? So let's visualize that. So let's say here is a good tree from the first iteration, and now, like, so this tree was sort of routing edges for us, right? So we were looking at fundamental cycles. If this was an off tree, we were looking at the entire fundamental cycle. And what does it mean for the tree to be good? That on average from this hidden cycle, on average, they were not too long, right? So most of these edge routings was good. So most of these fundamental cycles were good. So let's say some of these tree edges have changed. I'm going to take the next. Off tree edges can also change, but let's look at a tree edge. That's an easy case to understand. More to motivate what I'm doing. So let's say these dashed blue edges have changed lengths. If they became shorter, that's great. That's easy for us, right? So for sake of argument, let's assume they got very long. If they got very long, then I cannot use them anymore, right? Because they will destroy this property that these fundamental cycles are short. So I cannot use these dashed blue edges anymore, right? So if I can't use these dashed blue edges, but I can still use a partial routing. So this black part of the routing, right? This black part of the fundamental cycle is still a short cycle. It's strictly shorter than what was the previous one, right? So that's still good. So I'm going to keep these. I'm going to keep these black parts but now I've got a partial routing. I don't have a full cycle. I've got I've gone down to a smaller set. So here's how. So this sort of motivates that we want to think of, rather than think of just a tree, we're going to break it up and now think of forests, pieces of trees that are individually good, but they don't give us a full routing. Okay. So let's say these are the blue edges. The question now is, okay, sorry. So these are the blue edges. The black part of the routing is still good. They don't give you full cycles yet. Now, so the remaining question now is, how do I fix this tree? How do I fix this forest in some sense to get a tree that is good? Right? How do I patch this forest to get a tree that is still good? It won't be as good as before, but not much worse, slightly worse. That's our goal. To do that, here's how you can do this. So I've sort of just drawn an example graph. So these green are off tree edges. That black are the tree edges. Dashed blue are the edges that got much longer, and you don't want to use in the tree. Okay. So let me look at connected components of each of these. Right, so connected by these black edges. So these are edges of the original tree that you can still use. Look at the connected components. Those are good, right? These forest pieces are good. Let me look at them as connected components. Let me shrink them. Shrink them down to a single vertex. So every connected component gives me a single large vertex in what we call the core graph. Okay. And now your green edge that was going across now is going across vertices in the core graph. Right. So now I've got a much smaller graph to reason about or to work with algorithmically. I will find a low stretch tree on this smaller graph. Much faster because it's a much smaller problem. I'll find a low stretch tree, use that to patch the original graph. Right? And once you patch it, you will actually get a low stretch tree on the original graph. Right? The quality gets a little worse because now I'm doing it twice, or if you do it k times, your quality gets log n to the k. Right? But it's all factors we can afford.
So some of the key is that the size of the graph you can solve the problem on is proportional to the number of edges you updated.
That's exactly right. It's all right. So if I deleted k edges, I got k components and the size of the graph is same. Right? Okay. Thought you had a question.
No, I was just wondering. So, I mean, these are not transformations that you can do, right? I mean,
Good. You have to track them in data structures.
Yeah, okay.
Yeah. You can't explicitly write it down, but we track them in data structures.
You keep rerouting edges to like the super vertices.
Yeah, that's right. Questions about this idea of? So this is the vertex reduction idea that I was talking about.
So what do you actually store in the data structure?
Just have to sort of store which component you belong to.
And then whatever new.
So like then you get an implicit representation of this graph that you can work on.
So at any point of time, your data structure is like a collection of components. And I guess these green edges are also remembered. So
good. So right. So no, but green edges are just implicit from the moment I know what components these two pieces belong to, then that's enough. In fact, we will root them so everything also gets a natural label, which is just what is your root. So just storing the array of which components you are in sort of gives you an implicit representation to work with. Right, but this actually does not. I sort of cheated. You got fewer vertices.
just edges.
But we still have the same number of edges. So why is this faster? It's not yet faster. I have to tell you how to reduce the number of edges. Otherwise, you will not get a faster. Right? Good. So, but just a little before that, I think this I already told you that we are going to recurse on the score graph, find a lowest tree, use that to patch. You need what do you need to show? Right? So technically, I need to show that this size reduction is still preserving a good solution. So here's what we show, that if you had a good low stretch forest that you started with, then the core graph also had a good mean ratio cycle, right? You basically, we want, and the proof is sort of very, very natural. You take the original thing, you map it via the contraction, and you get. So some pieces of the cycle might get simplified as loops, but the loops you can just test and answer. Every loop I can just very quickly check its quality and answer. If none of the loops is good, then there must be still a good mean ratio cycle in this lower graph, right? Just sort of stating what we need to show as it recurs. I also there are other operations that I need to understand. Now this core graph is going to undergo edge updates, length updates, right? My lengths are going to increase and decrease. What does that mean? So this happened at one iteration. What happens at the next iteration? I built a graph and a core graph. At the next iteration, I got some edge that was deleted in the original tree. If an edge was deleted in the original tree, what happens to the core graph? So let's say here's the original tree and our connected components. These three blue edges were already deleted. and I had 4 components. If I delete one more, this blue dashed edge, I've broken down this single component into 2 components. Right? So on the core graph, this corresponds to splitting a vertex. Like this big vertex got split into 2, right? And the edges got split between. Right? So our core graph is now undergoing changes in terms of vertex splits and edge deletions. Like there are edge deletions that are already happening from the IPM. But because of the process of contraction, you're getting vertex splits. All right. So these 2 dynamic operations are happening, and every edge update sort of that happens. So you delete an edge in the original tree, you got a vertex split, but the degree of this vertex could have been very, very large, right? And especially if you have a small. If you went down from n vertices to very, very few vertices, your average degree has now gone up a lot. Suddenly, this operation of splitting the vertex is not cheap anymore. All of this has gotten very expensive just because you have too many edges. Okay, so we need to reduce edges for multiple reasons. You need to reduce edges. Okay, that's the second key piece in this data set is the edge reduction procedure. So the core graph construction is vertex reduction. Now I need to describe how do you reduce edges. We're going to reduce edges by building an explicit sparsifier of this core graph. What kind of sparsifier, right? So it's going to be a sparse subgraph of your edges. So I'm going to pick these blue edges, a subset of these green edges that approximately give you like not much longer embeddings. Okay, what do I mean? So here's a green edge that's not picked in the sparse subgraph. There is a path connecting its endpoints using only blue edges that's not much longer. Right? For every green edge, there's a path connecting its vertices that's not much longer. So it's now in terms of L1 length, right? Like so. Every green edge that I delete gets I'm picking a smaller set of blue edges so that you can use the blue edges to route the green edge without losing much in the length. Right? So this is what is called a spanner traditionally in graph. We want to maintain these spanners of reasonably good quality under these dynamic operations, edge insertions, deletions, and vertex splits. And we're going to do them even with explicit embeddings. What do I mean by explicit embeddings? For every green edge, I explicitly store, here is a blue path you want to take if you want to route the ends of the wheel. Right? Many existing spanner constructions did not maintain these explicit embeddings. We need them because we'll actually route them. And we need them to also be sort of low congestion. That if you route all the green edges, replace them by the blue paths, none of the blue edges get too crowded. Right? They only get crowded roughly as much on average because I'm routing from m edges down to n edges. So every edge roughly gets crowding m by n.
This somehow feels like the same k-stretch problem, except that now you're not asking for a tree.
Yeah, it is in roughly some sense. It is a stretch problem, not a tree. But right, yeah. But there's no vertex reduction that we're talking about here. Yeah, right. So finding a tree is exactly a tree. Yeah. Right. So technically, what happens to the good solution? Right. So what happens to the hidden short cycle solution, mean ratio cycle solution? So we show that if your core graph had a good mean ratio cycle, either this sparsified graph has a good mean ratio cycle, right? So the blue graph. So if your entire green graph had a good mean ratio cycle, either your blue graph has a mean ratio cycle, or one of the fundamental spanner cycles is good. What is the fundamental spanner cycle? Take a green edge, look at its blue connect it with its blue routing. That gives you a simple cycle in the spanner, right? One of these is good, or your blue graph still has a good cycle, right? So either you found it at this level, you just test all of the green edges for their embeddings. Either one of those is good, or you can recurse on the smaller graph. That's the technical guarantee. So I've shown you two pieces. The first piece is that you do vertex reduction, and the second piece is that you're doing edge reduction. I mean, remember all of these, they have to happen dynamically, right? At the top level, I'm changing lengths of edges, and right. So let's even forget the gradients. Let's say we're changing the lengths of the edges. As you change the lengths of the edges, your core graphs are changing, right? It's getting vertex splitting, edge insertions, edge deletions. You have to maintain both the core graphs and the sparsified core graphs under these changes, like very, very efficient. Okay, so here's so I have to maintain the sparsified graph under dynamic updates. Here's a theorem about the dynamic spanner. So ignore the degree constraint for now. Just a second. So you're given a graph that's undergoing edge updates and vertex splits, right? That's our core graph. That's undergoing edge updates and vertex splits. We can maintain a spanner. A spanner is a sparsified subgraph, right? With the following guarantees. Every edge not in the spanner has a path embedding that's not too long. So here's one way that it's different. In a tree, it's not a guarantee. Here we are able to guarantee that it's sure. Right? In a tree, it's impossible to get.
That's why you need a distribution in that case.
Yes. Yes. Two, we are able to explicitly maintain these embeddings. So every edge that's not in the tree, I'm not in the spanner, I know what is the cycle completing it in the spanner. Three, these have low congestion. So if you look at the blue edges, route all the green edges, no blue edge is a bottleneck, right? They all roughly get the same amount of congestion. 4 is now I need to maintain this as you change things. So there's you can change it in like as I delete edges, the amortized changes to the spanner is few. Some polylog words. Finally, is of course you can do. If you want to say you can do it efficiently. There's some issue with the degree that you need running time depending on the degree. It's not an issue in the final thing, but the theorem, the way I'm stating it, requires degree dependence. Right, and that's just because if I have a large degree, if I split that vertex, I have to do some work at that vertex. Okay, so this is the piece that maintains the edge sparsifiers. And it's like you have to succeed against adversaries, right? Because the answers you give affect the IPM updates, and those specific edges will get changed. So the next set of problems actually depends on the answers you give. So you have to work with an adaptive adversary. You can't work with obvious.
So can you go back
Yeah.
to the previous one? What's the point of 3? Like, where does 3 end up getting?
Good. So let's pretend otherwise, right? So what does this mean? So what is the question? Why do we need low conditions? So let me just show an image just for this one. So let's say in the blue graph,
particular edge that is used.
there's a particular edge that's say used by a lot of these green cycles. Now I delete that edge. How many embeddings will you change?
Oh,
I have to go and fix all the embeddings, right? That got broken. So maintaining low congestion really helps you in fixing it.
so it's implicitly used in the fact that you can do all of this and amortize low. Okay.
Right. Otherwise, the moment you delete that edge, you're toast. Right. So good. So now I want to just sort of collect these ideas. I mean, I know these theorems, I'm sort of not telling you how do I prove it, but these are our building blocks. Let me just collect these ideas to sort of give you a high level picture of what the data structure looks like. Okay. So remember, we sort of began actually with sampling a few trees, right? So the idea was that we're going to do a few trees. So here's how our data structure is going to look like. So you have the original graph at the top. We're going to call it level 0. At the original graph, you sample a few low stretch spanning trees, right? So log n low stretch spanning trees, that's a branching. From that, you got core graphs. After deleting the edges that got modified, you got our core graphs, that G by Fi. These are our core graphs that we got by contractions. To each of these core graphs, you apply the dynamic spanner. So now I've gotten sparser, smaller subgraphs, one corresponding to each of these trees. Right? And these, let's call these, so this is now level 1. Now I'm going to recurse. I'm going to, for each of these spanners, I'm going to again sample log n span trees. And go down some D levels. I mean, think of D as log n or just 100 if you feel better, right? So you go down some depth and recursion, and then there's a schedule for rebuilding each of these levels to get good amortization. Every time the number of operations you've dealt with is sort of the order of the size of the graph, you just rebuild the entire thing from scratch. Right, so that gives us our entire data structure. And roughly what's happening is that as you go down these levels, the size of the graph is shrinking. The number of vertices are shrinking, the number of edges are shrinking. By some like think what is k? Think of k as n to the 0.1. Right? My depth is 10. At every level, my number of vertices goes down by n to the 0.1 factor. My number of edges also goes down by n to the 0.1 factor. But sort of your branching is increasing. The number of instances that you're maintaining is increasing. So it goes up to log n to the depth, log n to the D level. What is the guarantee that this data structure satisfies? It says that at the Dth level, the expected stretch of a fixed edge is something like log n to the D or polylog n to the D. It goes with the depth, but the expected stretch is small over the entire collection of subgraphs. Right, and of course we need to maintain it over dynamic updates, edge deletions and insertions. Okay, good. So, and just let me reiterate, what are the kinds of solutions? So this is what we call a tree chain. So in this data structure, what are the kinds of solutions that we are looking for? There are two kinds. So this is not like in the original tree, we were just looking at fundamental tree cycles. Now we want to look at two of these, right? So just reiterating that you're maintaining this log n to the D trees. Okay, maybe there was a bit too much going on. I didn't tell you explicitly, but pick a fixed path down this forest. It is actually maintaining a low stretch spanning tree. Why is that? Remember when I showed you vertex construction, we had components, we contracted them, we got a smaller graph. If you find a tree on this, you patch both of these together, you've got one tree. Right? So now you've got D levels, you patch these D levels of forests and you'll get a single tree. So every graph, every path down this data structure is maintaining one tree. Right? So you log into the D trees that you are maintaining. So, and we show that one of them is good. Right? And what are the kinds of cycles that you would find? So we have two sets of reduction. One is vertex reduction, one is edge reduction. Each of those gives you some possible cycles to look at. So the vertex reduction, you look at all the loops that get created, right? So if you have a piece within, if you have an edge within a component, it gets collapsed to a single loop. You check the quality of the loop. If it's good, great, you're done. If it's not good, you throw it out, and then you're going down the loop. In the spanner, we had to look at fundamental spanner cycles. Look at a non-spanner edge, add it to the spanner, get a cycle, like with its embedding, look at the quality of that, right? So these are the two kinds of candidates that you have to keep looking at in the data structure, and we guarantee that one of them is good. And these can be checked efficiently because you're maintaining these embeddings explicitly. right? A spanner, we reiterated, and the spanner I have explicit paths. For every edge, I know how to route it. If I have the explicit paths, then I can check it very quickly. Right? So that's why I know. Okay, good. I think we are, sorry, we are very much over time. There are more details that I skipped. Adaptivity, I'll just say one word, because your adversary is adaptive. You give an answer, your next updates depend on it. So that introduces a host of issues in the dynamic data structure. But I will not say more about it. The key to solve it is that there is a hidden good solution. That turns out to be the key to solve adaptivity. But let me end at that. I'm sorry for going over time. Thank you.
Any further questions?
Is there an almost linear lower bound of this problem?
Well, if you sort of have to read the problem, that's a trivial, right?
Yeah.
So I don't know of anything more than that.
It does not.
So actually, here when you mean almost linear, what is the almost?
It's m times 2 to the log n to the 7x.
Oh, okay.
So I got it. So for specific applications of max flow, like max bipartite matching, did we know nearly linear time algorithms?
No.
We did not.
The best for max bipartite matching, the best we knew before this was m plus n to the 4/3 or m to the 1.48.
So actually nowhere close to.
Oh, actually, okay, sorry. It's a unit cost flow, so m to the 4/3 also. M to the 4/3 or m plus n to the 1.5.
See, and these algorithms also went via similar-ish techniques? Or
All of these algorithms have an outer IPM, right? And the right, so two of them I mentioned, right? M to the
If you want charts.
yeah. So for bipartite matching, there are sort of two I think that would be covered. This time to the 4/3. This is Katsuri, I'll use Stanford. 20. And then there is m plus n to 1.5. Then there is this very recently m to the 1.4. I guess that's not clear.
So these are algorithms for specifically for bipartite matching or general.
So this one is for unit capacity max flow.
Okay.
This one is for like they initially did it for unit capacity, but then they did it for general capacity. All of them use IPMs as outer algorithms. And in fact, both of them use electrical flows as inner algorithms. This one combines electrical and D-norm flows. So, right, so all of them are in this root M IPM regime, which is the standard, like sort of best used L2 IPM, not the Karnaker IPM. Root and Nesterov-Nemirovsky IPM. But they play tricks with. So this one plays tricks with the weights in the IPM to reduce the iterations from m to the half time to the 1/3. This is falling upon Madhuri's like the paths that Madhuri sort of started. The second one is some sort of data structure thing. So it reduces the cost of the iterations, inner iterations from all m to n and the number of iterations from root m to root n.
Okay.
And that sort of gets us. So there were some ideas about dynamic, like that the problems are related, they're dynamic, but they barely got below linear. But even, I mean, our algorithm, you say it's you wanted to only solve bipartite matching. It's not much simpler.
Right.
Like you sort of need, you still need all the pieces of the machinery. I don't know of a single piece to sort of leave out if you were going to do unit cost bipartite matching.
Further questions? So if there are no further questions, let's thank Sushant for the talk.